Chairman. This talk, it's going to be about the big word in multiaxial fatigue, which is plasticity. But actually, I expanded a little bit the scope of the talk so we can address also other challenges involving multiaxial fatigue. So, first of all, let me just very briefly talk about what we have already implemented in software in our university. So, for the multiaxial fatigue calculation, given the 6D stress or strain history, we actually like to work in the 5D space, which is much more efficient computation. And then an incremental plasticity algorithm uses kinematic hardening, isotropic, non-proportional hardening, and then we reconstruct the 6D stress or strain history. Then we perform maximum damage critical plane search. For case A cracks, just in the actual rainflow count is enough. For case B cracks, which are inclined with respect to the surface, then you might have to go to a modified Wayne-Brown rainflow count if you want to account for both shear stresses that happen in this plane. And if you have a non-proportional loading, that could be a little bit tricky, but it could be addressed. It's not a perfect method, but it works reasonably. Then what we do is we have to calculate an equivalent range for each rainflow counted cycle. We can use like a convex enclosure methods, ellipsoid methods. We use a moment of inertia method that we have been developing for a while because it can actually deal with non-convex paths. So it gets a better measure than other methods that only work well for convex paths in there. You can also estimate the non-proportionality factor, even though Tanaka's model has already done it here. We also use the moment of inertia method, but actually I'm going to show a better method today. And then you perform a damage calculation. The other approach we have implemented as well would be an invariant-based approach when actually you're mixing damage from different planes. And I think for methods this is not appropriate, or any kind of material that failed due to a single dominant crack. However, you might think that maybe concrete or some fiber reinforced materials that might have some distributed damage, then they might work. Just have to be careful with the hydrostatic components if it's really what's influencing your life or not. And also there's a straight path here trying to calculate damage without any cycle counting. I'm not bold enough to go there. I haven't found any reliable method going this path, but you could go trying to use energy there. So how do you implement that when you have notches? Well, it's first just a classical global local approach. Linear elastic finite element analysis to correlate the applied forces and moments to the pseudo stresses. You calculate it linear elastically. And then you use some local incremental plasticity to find the notch stresses and strains. So you need some elastoplastic correction. We use the pseudo-material approach, which is very good. We have to work with isotropic hardening, non-proportional hardening, Tanaka's rule, and you have to deal with kinematic hardening. And what I'm going to talk very briefly today is that multi-surface models like Munoz and Garuta are inadequate for most variable amplitude loading cases, and non-linear kinematic models are probably the best option we have available. So then we go for a critical plane approach. Materials that fail to a single dominant crack. For the case B cracks, when you have two shear components, you might want to do a rainflow that takes into account that it's a 2D rainflow. And then you have to find an equivalent range, convex enclosure. Don't work if the path is not convex. This moment of inertia method that you use is a little bit better in this sense. And the other way would be an invariant-based approach, like science mapping, for instance. But that's probably not quite applicable to both methods. Also, we have quite a lot of damage models. This is just a sample of the main stress-based model. We also have the strain-based and energy-based ones. And what we can see about them is that you have too many of them. And actually, one of the challenges is to have enough data to try to figure out which are the best parameters that should be included in these damage models. And all of them have also coefficients that need to be calibrated, the stress scale factors in there, which are different in each model, but in each model they are constant, at least for a given fatigue life. But one thing before we go on, just to make sure we have to make a distinction between proportionality and phase. So here you see tension torsion. This path A is proportional in phase path B as well, but with a mean stress. Path C is non-proportional out of phase. However, this path B here that doesn't go to the origin, it's non-proportional, but it's a mean phase loading. It's a mean phase loading with different mean stresses that make actually this principal direction vary. And on the other hand, if you have a biaxial tension, you can have a proportional loading because the principal directions are x and y, but it's out of phase. So you can get anything. So they are kind of independent. So you have to be careful when talking about proportionality and phase. About incremental plasticity, we work on the reduced order space, the 5D space instead of the 6D that many places use. Many people also work in 5D, but we work in 5 dimensions in the entire calculations, from the plasticity to consideration of non-proportional hardening and so on. And the nice thing about this specific projection that we work on, it's very easy to work in 3D or 2D if you have free surface conditions, even including surface pressure. The other rates, I mean, probably besides being more efficient computationally, probably the best thing is that you guarantee plastic strain compressibility, which the 6D model, due to numerical errors, this might be violated after a while. All involved equations are almost identical to the 6D or tensor formulations. For instance, the yield function in 5D is very simple. It's just a very simple equation without a scaling factor there. Like the plastic flow rule in 6D and 5D, they're exactly the same. Even the generalized plastic model are the same. So the direct problem, the inverse problem, when you get stresses from strains or strains from stresses, they are identical. So basically, if you already have implemented some incremental plasticity code, you don't need to change it. Just change your vectors from 6D to 5D, because the equations in 6D and in 5D, they are going to be the same. However, now we have to deal with hardening. And the way we do that, we have isotropic hardening, expansion contraction of the yield surface. Actually use a very simple model with one fitting parameter. There are models with more fitting parameters, but we try to use the fewer possible that still can describe the transient effects. And also we implemented also very simple strain rate internal effects with only 2 adjustable parameters. That works reasonably well, especially at least for some simple cases. Regarding non-proportional hardening, you have the additional hardening coefficient, which is a material parameter, but actually has some strain level dependence, stress level dependence, and the non-proportionality factor, which only depends on the loading. And so far, Tanaka's model is the only one that can correctly predict this non-proportionality factor, including all the transient effects, which are very important in the presence of overloads. We actually use the polarization tensor. So these are the equations that we've implemented to calculate this non-proportionality factor. This is the differential equation of this non-proportionality factor. And this slide is a very nice one. What we did, we got Tanaka's model and we solved it for periodic history. We integrated it, and actually we could get an integral form for the non-proportionality factor of periodic history. So actually, if it's a polygonal path, like you have a discretized path, it's actually just a very relatively simple summation. And the nice thing about this, first of all, it's considering the plastic strain path, not the stress path, and not the total strain path. So it actually is considered what's the driving force of this hardening, which is the plastic strain. The other thing, it's exactly reproduce Tanaka's model in the steady state. So if you assume Tanaka's model is the best, this should be the best estimate for periodic history. For non-periodic histories, of course, we need to solve the differential equation there. And the thing is that for the plastic strains, you probably need some incremental plasticity model. Professor Sousa has talked that some people find it easy, some people find it difficult. My point of view is that it is easy after you've thought about it at least 10 years. So I think the short answer is it is difficult, unfortunately, but you get used to it. One issue with non-proportional hardening models is that all of them especially Tanaka's model, they predict non-proportional hardening for a cruciform specimen. And that's not supposed to happen, so this is one thing that we might want to improve in these models, or even maybe check if in some cases you might have a little bit, but supposedly if it's called non-proportional hardening, why would it happen in a proportional load? About kinematic hardening, translation of the yield surface, also in fact, actually have very simple rheological models that can explain it. And Miraz did a very interesting contribution a long time ago, where he actually puts all these spring slider elements in series, and he could describe the stress strain behavior. And when he did this in multiple dimensions, he actually got an incremental plasticity model. So there are actually parallel linear spring slider elements connected in series. So these models, they can only be used for balanced loadings. So if you don't have significant mean stresses, then they do a really good job. However, they can predict some false unstable ratcheting for significant mean stresses, which is a model shortcoming. This has been included in several other papers, and not a numerical error. Moreover, the linear formulation cannot predict uniaxial ratcheting or mean stress relaxation, so you have some defects there. But probably one of the worst of them is when you have a neutral load. Actually, if your stress state is going around the active surface, you're going to have a yield surface that translates with zero plastic strain, which is nonsense. So it actually predicts a zero plastic strain in there. And this limitation really makes us have to use nonlinear models. And then nonlinear kinematic models, they are series nonlinear spring slider elements in parallel. So the main difference between this and Miraz model is that here you have series elements in parallel, and the other ones you have parallel elements in series. And the other difference is that here the springs are nonlinear, and in the Miraz they were linear, with piecewise constant, the general plastic model. And here we can predict both uniaxial and multiaxial ratcheting. We also, since we are working on the 5 dimensions, we also propose a 5D unified surface translation direction, which is just an equation that combines all translation directions that have been proposed, I mean most of them, at least the most famous ones. And so this single equation can reproduce since Praga's 1949 until Chabosh. Even the Miraz model can be reproduced here, Jiang's, and also some more recent models. They're even better than Jiang's model because they can independently calibrate uniaxial and multiaxial ratcheting. So we just implemented this equation, and it's very easy to switch rules. Not going to talk much about two surface models. They are a very simplified version of incremental plasticity, and they combine properties of the nonlinear kinematics and of multi-surface models. So this, in the paper you're going to see this comparison. They can be very good for anisotropic materials because you can work with very complex surface. However, they only have two surfaces, so they have limited memory, plastic memory ability. If you're going to work with complex variable amplitude loads, it's not a good idea. You want to work with more than that. So basically, you want nonlinear kinematic models. But now you have a notch. How do you correct for the notch plasticity? One method is the incremental model approach. And this approach, when we formulate it in 5D, we solve the problem of the plastic strain and compressibility that could be violated in 6 dimensions. However, this formulation is only for monotonic loads. Once you go to cyclic loads, you actually need some memory value, the less reversal, so you can calculate and equate these values. And this is an undefined problem because how do we define the reverse in multiaxial loading? There are many proposals, but none of them works well in here. I can get a counterexample for each one of them. And also the other thing is that the system of calculations, when you solve them in an implicit model, it can have multiple solutions. So I don't like it. I like it very much to the material approach. It can also be implemented in 5D. The pseudo-strain rule can be implemented using the same surface instead of the same plastic strain levels. And this way you can solve it in a single pass without having to solve it twice. With pseudo-stress, it has also been shown a long time ago that it could also be solved in a single pass if there is no surface pressure. And we can also deal with large gradient effects if we replace KT in this calibration with a proper KF, and then we have several proposals that have already been talked here in this conference. So let me talk briefly about our experimental system. So performing tension torsion experiments on 316 L stainless and 775 aluminum, kind of the streams of non-proportional hardening. We have a very extensive experimental program going on. So we have studied the amplitude effect of non-proportionality, the non-proportionality factor, multiaxial ratcheting, mean stress effects, shape of the path, square or circular, cross and X-shaped values which can fool several different models, and even a path that Professor Sousa proposed in his book that we kindly call the Maltese cross, which is a very challenging one, and we've been able to simulate all of them. This, for instance, is the path for the square path, and actually if you use a linear kinematic model, it works very nice, even including non-proportional hardening in there. The interesting thing is that all the simulation we're performing 2D. So once you use that 5D subspace, you just remove some lines from the vector, and you can perform all the simulations in 2D, not in 6D and then extract the values. So these are very fast. We also did some simulations with other graph sources, for instance, experimental data, and actually what you can find is that the non-linear kinematic models, they can deal even with mean stresses and mean strains, and it does a really good job. Actually, all this is very reasonable, but as Professor Fatemi said yesterday, is it enough for fatigue predictions? I don't know, we are very sensitive to the stress amplitude, so we might need to improve or use a few more parameters in there. This is one of the unknowns that we have. So let me show 2 slides. One is what I think I know, and the other one is what I know I don't know. So what I think I know is that incremental plasticity should be calculated in 5D, 3D or 2D subspaces. It's much more efficient, and you guarantee plastic strain compressibility. We have some details in the book that we're about to publish, and we describe this very in details. The 5D unified surface translation group, makes it easy to switch these hardening models. Miraz-Garut or 2 surface kinematic models should not be used in variable amplitude loading with significant mean stresses. Non-linear kinematic models can handle non-proportional variable amplitude loading, balanced or unbalanced, and they can also predict ratcheting, and even with some really relatively simple terms, predict also thermal, creep, and strain rate effects. Tanaka's 1994 non-proportional hardening model still is the best available. Don't know if it's because it's too good, or maybe we haven't worked hard enough, because it has some issues, you see. For the cruciform specimens, it predicts non-proportional hardening. For non-plasticity corrections, incremental model is complex and unified, pseudo-material is simple and effective. Critical plane damage models should be used for metals, not invariant space models, because they mix damaged planes. So if you fail to a single dominant crack, you should go for some critical plane approach. And multiaxial adhesives should be filtered wisely. So don't miss Professor Jami's talk just after the coffee break. He's going to talk about a multiaxial racetrack filter. So this is now what I know I don't know. A few challenges. For instance, how many hardening parameters are enough for fatigue? And how much do I need to sophisticate my plasticity model to get good precision, not only in the stress level, but also in the life level? How do you define the reversal in multiaxial fatigue? I mean, the incremental model rule needs that. How do you define that? Is there any non-proportional hardening in biaxial tension? There shouldn't be. Then which model should be used to correctly account for non-proportional hardening if all the available special Tanakas predict that, and this would be a source of error? Should damage models be separated into tensile and shear, or should they combine both shear and normal ranges? Actually, we see the more recent models that you're combining shear range and normal range in the same parameter. You don't separate this search. So should you separate or not? In this case, how do you compute rate flow of these different quantities? You cannot use von Mises in them because they're going to be used separately in the equation. Which material should you use an environment-based damage approach and not the critical plane? I mean, concrete, some fiber reinforced. So which ones metals should use probably critical plane, but which ones shouldn't use, which ones you have distributed damage. How do you calculate equivalent ranges of non-convex cycles? I mean, we use the moment of inertia method, but also all the other methods, even the Novostilov's integral and the convex enclosure methods, they can only deal with convex paths. They don't work very well with non-convex one. And finally, what I think is the holy grail, is it possible to define an incremental damage model that accumulates damage in real time without cycle counting? So you have, I don't know, damage surface, and you go with your stress and strains, and as you reach new damage values, you keep increasing them, and you have an increase in damage. I've seen some models like this, but they're not reliable. Can we do them? So, thank you. These are what I don't know.